3D cameras, such as LiDARs, are a key technology for 3D computer vision, being used in fields like robotics, augmented reality, and autonomous driving. Typical 3D cameras capture high-resolution 3D point clouds, which are fed into computer vision algorithms to do things like track human pose or map the environment in 3D. Recently, a class of low-cost, miniature LiDAR sensors has emerged. Just like a typical LiDAR, these sensors report the distance to the scene at each pixel, but these sensors are much lower resolution, for example 4x4, 3x3, or even a single pixel. Given the very sparse signal from these sensors, existing computer vision algorithms do not perform well. So, how can we make use of sparse, low-resolution measurements? In our paper, which will appear at ICCV 2025, we take a step towards answering that question. We show that, given a distributed set of as few as 15 single-pixel 3D sensors, it's possible to do parametric scene recovery. Parametric scene recovery is a common task in 3D computer vision. In general, it utilizes prior knowledge about the scene to simplify the task of reconstruction. For example, if we know that the scene contains this object, but we don't know where it is, we can treat the object's position and orientation as parameters that we seek to recover, rather than reconstructing it from scratch. This exact formulation is called 6D pose estimation. Parametric scene recovery encompasses other problems as well. As another example, if we know the scene consists of a human hand, we can aim to recover the shape and articulation of the hand, and similarly with an entire human body or the body of an animal or a robot. To understand how our method works, first we need to explain exactly how these miniature time-of-flight sensors operate. Just like a typical LiDAR, they utilize the time-of-flight principle. They illuminate the scene with a very fast pulse of light, and measure the time it takes for that pulse to return back to the sensor. Notice that not all of the outgoing light returns at the same time due to differences in scene depth. Fortunately, the sensor captures the intensity of returning light over very fast timescales, allowing us to separate the signal from different scene depths. This captured one-dimensional signal is called the transient histogram. Say we have a distributed set of miniature time-of-flight sensors all looking inwards, and we know the position and orientation of each sensor. How can we use these sensors to estimate the 6D pose of an object in the scene? Instead of relying on point clouds, which are too sparse to work well in this setting, our method utilizes the entire transient histogram. Given a fixed set of sensor poses, we train a neural network entirely on simulated data to estimate the underlying scene parameters, in this case 6D pose, given the transient histograms from each sensor as input. Then, we iteratively refine the prediction from that neural network using a differentiable analysis by synthesis pipeline. At each iteration, we render what we expect the measurements from the sensor to look like, given the current estimate of scene parameters. We then compare the rendered histograms to the captured histograms via a loss function. We take the gradient of that loss function, and the scene parameters are iteratively tweaked via gradient descent to minimize the difference between the rendered and the captured histograms. In the end, we get an accurate estimate of the underlying parameters, which utilizes the entirety of information captured by each sensor and takes advantage of the sensor's wide field of view. For more details and quantitative results, see the paper. Now, we'll show some qualitative results. First, on 6D pose estimation, with 15 sensors distributed around the scene in this configuration. Here are reference images of various 3D printed objects placed on a tabletop. And here are the predicted poses from our method, utilizing only 15 time-of-flight pixels. We placed each object at a total of 25 different random poses. The one you're seeing here is the pose that led to the median error for each object. Similarly, here are reference images for more realistic 3D objects. And here are the poses predicted by our method, using the same 15 time-of-flight pixels. Again, the object pose which led to the median prediction error is shown. Notice that the can of Spam in the rightmost column is a failure case for our method. The specular surfaces on the top and bottom of the can make it hard to model the time-of-flight measurements, and the small, near-symmetrical shape makes the refinement module inconsistent. In the paper, we propose some ways of addressing these limitations in the future. We also build a prototype for hand pose estimation, in which 8 sensors encircle the wrist. In this case, we aim to estimate the shape, articulation, and relative position and orientation of the human hand. For hand pose estimation, we find that the refinement module is not effective due to unmodeled effects at very close distances, so the results shown here are just for the feed-forward network, which has been trained on simulated data and fine-tuned on some real data. Let's look at some qualitative results. First, 2 success cases. You can see that the method differentiates between an outstretched hand and a pointing hand. Next, here is the pose which led to the median error. The overall pose is correct, but the alignment could be improved. Finally, here is a failure case. The two extended fingers are confused for one, likely because the resulting signal in the time-of-flight sensors is very similar. While still in the prototype stage, our approach has great potential for 3D vision applications that benefit from low cost, low power, and distributed sensing, such as wearable computing for gesture-based user interfaces, and robotics equipped with distributed arrays of sensors able to reconstruct the environment in all directions.